Hello, and welcome to KAUST Live. This week we're talking about deep learning and how it's helping speed progress towards the realization of, among many things, fusion energy. Here to speak to us about that is Princeton Professor William Tang. Professor, thank you for joining us.
My pleasure. It was quite an adventure to come this far to KAUST, but it's been a very stimulating visit already, and I really am grateful to my hosts here for preparing such a very bright, inquisitive audience and a quite large one, and so I look forward to further discussing the topic of interest here with you.
Yeah. Well, so you had a lecture yesterday, so tell us a little bit about what you spoke about.
Okay. The main topic of the lecture is to talk about a very exciting application domain for the general arena of machine learning and a special type of machine learning called deep learning. And this all fits into the artificial intelligence category. And artificial intelligence, just to make things more simple, is just using machines to help us carry out very statistically based analysis very rapidly. And the application domain of interest here is the development of clean energy for the world. And the kind of energy is fusion energy. It's been known for a long time. Fusion energy in the most natural state is the sun. The sun produces its energy that way. And uncontrolled fusion reactions would be like a hydrogen bomb, but for peaceful purposes you're operating at much lower densities, and that's why it's such an attractive energy source for many reasons. The raw materials that you need to have a fusion reaction are just the isotopes of hydrogen, which are abundant in the oceans, and it also doesn't have any of the dangers usually associated with nuclear power, like nuclear proliferation or big disasters like 3 Mile Island, Fukushima, the most recent example. And so with a lot of advantages and very few disadvantages, the sort of cynical comment about fusion has been, it's the dream energy source of the future and always will be. It's always downstream. But in the presentation that I gave yesterday, I started out by first explaining, what fusion is, what's involved there, but also the fact that the progress in this area has been quite steady since about 1975 or so. And if you plot a straight line plot of the different greater achievements along the way in terms of delivering fusion power in the laboratory compared to how much energy you put into the system to deliver it, this ratio went from a very, very tiny number to, by the mid-90s at Princeton actually, where we put deuterium and tritium as the main components of the fuel, and delivered a ratio of about close to a quarter, 20%. And that was a huge breakthrough for fusion, and was headlines of all of the big newspapers and such, a lot of excitement. The international community was also very stimulated, and they also had parallel projects at that time, most notably in Europe. The Eurofusion Consortium, made up of the European nations, Germany, France, the UK, and so forth, delivered in their device, which is more powerful and also very well built machine, on a comparable scale, but a little larger. The one in Princeton, even in the dollar amounts invested in those days, was close to $1 billion. And so this is in the mid-90s or so. So the Joint European Torus people move from there almost to break even, which is close to 1, but around 0.8 plus. And so that gave people the motivation that, wow, okay. And by the way, that straight line, the slope of that line is steeper than the Moore's Law line, which is a measure in high-performance computing of how fast things are moving. But unlike Moore's Law, where you're able to deliver more and more capable laptops and things along the way. There weren't really distinctive sorts of products along the way. And so to sustain this, you had to look at the tangible progress that's being made. And the next natural target was to go from the accomplishments of the break-even period to this big international facility called ITER, I-T-E-R. And this is a huge international consortium made up, populated by 7 governments representing over half the world's population. And it is now hosted in France. And the progress is moving forward in a steady way towards a first plasma by 2026, roughly. And this will be a burning plasma demonstration. And to acclimate the crowd a little bit to, or the audience a bit to, what does this mean if you go forward to a device like ITER, which has as its goal, remember I said the Eurofusion jet experiment was able to achieve near break-even. That's like of order unity. So ITER's grand goal is to go up to a factor of 10, well above break-even.
So contributing energy back to the grid, or even being able to sell
well, not quite back to the grid, because this is a demonstration that you can sustain such a constant delivery of fusion energy, exceeding the amount that you put in by a factor of 10 or more. And that's a good question, you know, leading up to the analogy that people usually ask you for, well, how does this compare to other arenas that have moved towards modern progress? And so if you think about aviation and you think about what the Wright brothers were able to achieve at Kitty Hawk, well, the plane flew, okay? That was a big breakthrough. And you can see what's happened in the course of time with respect to aviation. But had you interviewed the Wright brothers at that time, they would not have been able to tell you, well, we're clearly going to exceed the capabilities in transportation of trains and boats and so forth. So there was still a lot of technology to be developed moving forward. And so too will this path towards clean energy, fusion energy, also can be expected to take time. And so ITER is an experiment. It's called a burning plasma experiment because it will be in a thermonuclear regime, you know, where and there'll be more modern magnets than was deployed for the Joint European Torus. And these are superconducting magnets that will sustain a pulse for a much longer period of time. And these are all technical sorts of things that we believe are achievable. But the thing to keep in mind, though, is that you're confining a very hot gas of charged particles. Plasmas are also called the fourth state of matter. And, you know, I said at Princeton in the Department of Astrophysical Sciences, and the reason that it sits in astrophysical sciences is because plasmas make up over 99% of the visible universe, ergo astrophysics. But this is a very different application domain than cosmology and other grand challenge areas. But this has a very practical goal to deliver a source of clean energy. And progress along this line, just to cut to the chase a bit, is impeded by the following, that Mother Nature doesn't want to sustain a very hot gas, keep it in place, confined by magnetic fields. Because it's such a hot gas, you can keep it confined from touching the walls and such that surround the medium with a very ingenious design of a magnetic field, because charged particles interact with a magnetic field. And the goal is to sustain density and temperature, multiplying a triple product with the confinement time. How long can you keep it all confined? Exceeding a certain number called the Lawson criterion. And if you're able to do that, then that's the grand goal for fusion. But confining this hot gas of charged particles with Mother Nature acting very, very effectively to try to dissipate the confined energy is very challenging. And one of the fastest ways that the plasma escapes is through these very rapid sorts of large-scale disruptive events. These are kind of like instabilities that build up, and if you cannot curb these, in other words, you have to be able to predict the onset of these disruptions, and you have to do it very accurately and very quickly. And the criterion that the experimental scientists and the machine designers made was you have to do this with better than 90% accuracy predicting the onset of these disruptive events, with less than 5% false positives, like you said, oh my goodness, it's coming, we have to shut down the machine. You can't afford too many of those. And then you have to do everything at least 30 milliseconds before the disruption occurs. If you do it 10 milliseconds before, you can do it more accurately, but it's not good enough because you're already on the slippery slope and you don't have a way to avoid the disruptive event.
Yeah. Well, for you personally, what came first, the physics or the computer science side of things? I mean, you seem to have brought two sort of distinctly different areas together with this. So how did that become part of your research life?
Okay, that's a very good basic question. I was trained as a theoretical physicist, and then I got more and more involved with high-performance computing as a natural tool. You know, that's a natural thing that you would expect. You move from the abacus to the slide rule to laptops and so on to supercomputers. And similarly, if you so you want to solve the problems, and you want to solve the challenging problems before you. And as a physicist, you know, you definitely are strongly attracted to that area. And then as the problems, the complexity of the problems became more challenging, then it was a natural thing to look at, are there new methodologies, new approaches that can transform the way that you're working now? And so that brought me naturally into being very interested in the machine learning approaches first, to complement the predictive capabilities out of conventional first principles based theoretical models that can run on supercomputing platforms. But you needed more than that to solve a key problem like this one. And so that's the nature of the natural progression. And I think all scientists really need to be able to be to constantly question what is the best approach that can accelerate progress. Even if you're in a very comfortable comfort zone and you've done real well, you know, in establishing your reputation. And this is what the element of bringing in really super bright young people into the arena brings, because they want to establish their track record and they see opportunities. And a lot of this is semi-virginal territory in terms of how much you can bring into play. And one of the things that is a big challenge is that you want to merge the high-performance computing capability through conventional applications of supercomputers to machine learning and deep learning. And for the big supercomputing centers, they also want to be able to simultaneously address, you know, how do you design the machines better to handle both?
Talk a little bit about co-design. I know that that's a interesting area in your field right now.
Yeah, that's a really good question, and this is an area that my host here, David Keyes, and I were involved in about a decade ago in terms of cross-disciplinary benefits from bringing together. In those days, it was computer science, applied mathematics, and applications, a variety of applications, and bring them together in such a way to make cross-disciplinary progress. The thing I was mentioning, you know, cross-disciplinary, if you can identify those things, it's great for accelerating progress. And then you asked about co-design. That's a new element that came along a bit later, because the design of more and more powerful supercomputers, we're already seeing a variety of these things coming up. And so if you can couple the existing activities in this cross-disciplinary program involving computer science, applied math, and applications, and you add the element of how does this impact, how can you best utilize the new machines being designed? So co-design between the machines as well as the scientific domains buttressed by applied math, computer science, and different application domains. And so that's a key element in everything that's done moving forward, because there's lots of different approaches right now, world-leading approaches. And I started to say at the beginning, you know, NVIDIA has really helped us accelerate progress by giving us access, and they are the leading facility right now approach for accelerating deep learning progress. But believe me, you know, the other major companies like Intel are not sitting on the sidelines. They're coming up with new approaches, new designs that will be different than GPUs. I'm currently involved with our team with a exciting new project that is Intel-based that will be featured at the Argonne National Lab. It's called the Aurora 21 Exascale project, and it will be a completely new Intel-based design, and a lot of it is under non-disclosure agreements still, and so I can't talk about the details of that yet, but I know enough about it to know that this approach looks very competitive, and that's great for the application domains, you know, because you know darn well that there's going to be progress and evolution of designs in the architecture and so forth. And so this leads you to another thing, which is something that I've always believed in and try to practice, which is even before the machine learning, deep learning things, you try to structure your discovery science software to be machine portable, architecture portable. You can go from one design to another. And that's very wise, considering that for a while, you know, it was CPU dominated, and then the GPUs came along, and if you're designing your software to only use the CPUs, and you didn't look ahead to see the incoming wave that the GPUs brought with their accelerators, then you're left in the lurch, and you really have to do some hard work to catch up. So if you try to keep cognizant of the different approaches, different architectural approaches, which comes into play with the co-design thinking, right? Then you can get ahead of the curve a bit, and so that the transition isn't so wrenching, you know, that, oh my God, we've got to totally redesign our software suite. Right. So that's another benefit of co-design.
How is big data and extreme simulation, how are those two things being combined to sort of cover over the weaknesses of each of those approaches?
That's a really excellent question, and it's an ongoing challenge right now, because the various governments, you know, in the US and Europe and Asia and so forth, they're all struggling with this particular challenge, you know, this convergence, if you will, between big data, machine learning-based challenges going forward, and the conventional path to extreme scale supercomputing. And so there's no one sweeping answer for all of this, but the practical way to go forward in a series of workshops and things that have, international workshops that have moved forward in this area that have been led by Jack Dungara, Professor Dungara from the University of Tennessee. A number of us have participated in that, and we bring up our own exemplars of you know, example cases. And in the case of the fusion energy application, there is a good example for how you can do this, and we're going to do this more and more. So, as I said, you have the basic workflow of the big data, you know, the observed experimentally measured data. You know what your target is. You want to avoid these disruptive events. The data is related to the disruptive events. They're connected by these classifiers, these pre-disruptive event classifiers that are known to exist. You know, you can observe these experimentally, but you can improve those predictions. You know, right now, as I said, the field was constrained by relatively simple versions of these classifiers because you couldn't do dimensional analysis for one, like, you know, going to 1D and 2D signals. And so now the door is open for that. So you can bring in more relevant, realistic, pre-disruptive event classifiers that our experimental colleagues say, yeah, we can see these things, you know, and our response was, but we can't involve those because we don't have the tools to bring in the higher dimensionality signal absorption. Now we have. And now we can look to our high-performance computing colleagues, and I'm involved in some of that too. So I can speak to the excitement and the potential in this area. You can now explore much more realistic sorts of phenomena that are pre-disruptive phenomena that you can then put together reduced models for, guided by these high-performance computing results. And these are reduced models of things that you can do that, but you don't need more than reduced models. This is just improved models that help you with the classification of the phenomena that you're looking at. So any new insights in this area will help that formation, and the high performance computing side of the thing will give you the most realistic manifestation of that. And to integrate all of that is going to be a challenge, right? But at least you see a possible convergence between these main themes. So that was a very good question, but the convergence of big data, analytics, machine learning and such, together with the conventional path to extreme scale supercomputing in different application domains, is a very real sort of path forward to improve things.
You're probably one of the best positioned people to answer the question, if time and money and energy resources and everything else is not an obstacle, what is the machine of the future that's going to solve some of these next generation plasma questions, for instance, or cancer questions or whatever? What is that machine that you build 20, 30, 50 years in the future?
Yeah, that's a really super challenging question to predict the future about how fast these, first of all, the technology will move, you know, to enable you to do more and more aggressive simulations. We have yet to do these on, you know, exascale machines as yet, you know, and we'll soon be able to do some of these applications. For example, on the #1 machine at Oak Ridge, you know, they can develop exaflops of performance, and this is fine. You get a little preview of what might happen. But in a lot of these cases, they're not yet talking about moving from prediction to actual control, okay? That is embryonic, you know, in terms of demonstrating the capabilities in this area. And I'm personally very excited about this, you know, the deployment of our predictors, better and better predictors, onto an actual real live machine. And now you're going to bring in other aspects of the theoretical description of how you use statistical prediction methods and applications like inference and reinforcement training and so forth, reinforcement learning. And so you're going to need a lot more of this interdisciplinary collaborations, interdisciplinary here between the experimental people that design the detectors and so on and so forth, and your statistical people that are making the predictions. Because the challenge then would be you're deploying your better predictors based on machine learning sorts of methods onto an actual plasma control system, you know, a real live plasma control system. And what are you going to do? You know, you can right now, the evolution of progress is you're using very brute force methods to shut the plasma off before it can disrupt. And that can be very costly, and you don't want to do that if you can do better. ITER is not designed to or isn't expected to be running until 2026, and so you have some time. The hardware design is not going to change much, you know, for the machine between now and then, but you do have time, and you should use that time to embrace the 21st century technology to help steer your way, right? And this is an exemplar. In the cancer remediation area, there are different protocols that one can design for and implement. Then you have to go through the FDA approvals for even protocols and such. So it's a work in progress, right? But it's exciting because you see a path forward. And so how much time exactly, it's just an educated guess at best when you achieve your goals. But the thing I'm encouraged by is, number one is that if you're talking about money, investments and such, you already see the examples from industry that machine learning, deep learning, AI is just a huge benefit technologically. And whether you can absorb those into your specific application domains like clean energy, cancer, climate predictions, lots of things. It's just very exciting. The other really exciting thing, and I keep emphasizing this, is the influx of super bright young people. And they're coming in younger and younger. Like even this past summer, I had the pleasure of acting as a mentor to a super bright high school student that came in that's going to be applying for colleges next year. And it's amazing how fast they can absorb some of the basic concepts. And then we have like undergraduates and of course graduate students that are increasingly interested and engaged in these areas. So that, that all combines, the increased interest from the governments to fund these areas because of the imperatives from the missions that you have to deliver on. You can't do it with smoke and mirrors, like in clean energy fusion. You've got to make a machine like ITER work. And the other analogy I give sometimes is if you're building a house, you can do certain problems like making sure it's well insulated and such, and the associated science that goes into that using high performance computing is great, and so you'll have a better and better insulated house. But what good is it if you build your house on an earthquake fault, right? And so you better get rid of that first, make sure that your house is free of an earthquake area, and then you can contribite to making it a better and better insulated building. And so I think there are many interesting examples as you move forward.
Do you feel then that specialization of these amazing supercomputing resources is going to be the future, or are they going to continue to be sort of generalist machines that are applied to certain problems?
That's a really good question, and it's a big question that the supercomputing centers must answer. And centers, even like here you have Shaheen, it serves a significant community. And you cannot just say we're only going to concentrate on these biggest grand challenge problems. Then you leave behind very interested faculty, students, and so forth, who are developing their own lines, maybe not to this level of maturity yet, but you want to continue to improve that. And so it's not a one-size-fits-all sort of thing. There's some outliers, if you will, that can use the most powerful systems at scale, but other application domains that can make perfectly good progress without the extreme scale computing, even for exascale computers without the machine learning component. And so, I mean, a simple way of saying that is if your problem size is not huge, then you don't need all of this. You don't need a sledgehammer to crack a peanut, right? So, one needs to then do a proper balance, if you will, between what you're going to support and and I think that'll happen quite naturally.
Well, Professor Tang, we really appreciate you taking time to sit and talk with us today.
It's a great pleasure. You asked great questions. You steered me in the right direction, and I hope this is all digestible and understandable.
Absolutely. Absolutely.
And so it's a great pleasure talking to you.
Absolutely. Enjoy the rest of your time at KAUST.
Thank you very much.
Much appreciated. And that's all the time that we have for today. Join us every Wednesday at 4 as we explore the people and the science that make KAUST unique. Remember to comment, like, and share on all the KAUST social channels. And from everyone here at KAUST, thank you for watching.